Hello everyone, welcome back to the series of tutorials on geostatistics. Today we'll learn about interpolation of objects in Hilbert spaces, and we'll illustrate this concept with a practical application in climate sciences. Suppose that we are given three functions, f, g, and h, at specific locations in the map. For example, imagine that these functions are time series of temperature data measured at meteorological stations in Brazil. So I have one station here where I measure the function f, which I'm drawing here as a curve coming out of the page. I have a second function g and a third function h. The question that we now have is, how can we estimate the full function or full time series at a new location marked with an X here in the map? The framework that we're going to describe in this tutorial has been proposed by Alessandra Menafoglio and others in 2013. If you're interested in more theoretical details, I highly recommend reading their work. Here, we consider a collection of k georeferenced objects, zs1 through zsk, these functions, for example, which all live in a Hilbert space H. A Hilbert space is nothing more than a vector space with an inner product. S1 through sk are the coordinates or locations of these objects in a geospatial domain D, which can be the 2D map or the 3D subsurface of the Earth. For example, we can be interested in interpolating vectors with D components. So our Hilbert space is Rd, and these objects, which are vectors with D components, have a usual inner product. So the inner product between a vector x and a vector y is this summation of the entry-wise product of their coordinates in their canonical basis. Alternatively, we may be interested in interpolating functions. So we take this Hilbert space as the space of square integrable functions, and then we define the inner product via integration. Our goal is to define an estimator of the object at a new location S as a weighted combination of the available objects. So we want to find the set of weights lambda 1 through lambda k, which can be used to weight and combine available objects zs1 through zsk. Notice that this estimator is defined in terms of the scalar multiplication and the vector addition in H. And so you might ask, why do we need the inner product? Recall that the choice of the inner product induces a norm, a distance, and consequently a notion of variance in the Hilbert space. This means that the universal Kriging system of equations can be generalized to Hilbert spaces to find the set of optimal weights. So we want to find a set of weights, lambda 1 through lambda k, which minimize this variance of our estimator minus the unknown value, which is the value that we're trying to estimate at this location S. We do this minimization subject to the unbiasedness constraint, which is saying that on average this estimator gives us this mean field. This mean field here is a function that takes a coordinate and returns an object. In this case, it can be a function, a vector with D components, or any object in a Hilbert space. This term is known as the drift term and is usually a linear combination of monomials in the coordinates. So I have functions, which are just monomial terms in the coordinates, and I have coefficients a sub l, which are now objects in this Hilbert space. In practice, this theoretical development leads to two main changes in a modern Kriging implementation. First, these coefficient objects, a sub 0 to a capital L, they must be estimated with an implementation of generalized least squares that supports Hilbert spaces. So I can say that I have a vector z of objects, zs1 through zsk, and I want to take a linear combination of these objects to get new objects as my coefficient objects, alpha sub 0 to alpha sub capital L. The second change that needs to be implemented in order to generalize an implementation of Kriging to Hilbert-Kriging is that the empirical variogram must be estimated in terms of the induced norm in H. So when you look at the expression of the empirical variogram that we have covered in previous tutorials, we will need to replace the square difference by the norm of the subtraction of these two objects. So this is a function minus another function at a different location, and then I take the norm of the resulting function. Fortunately, all these details are sorted out in GeoStats.jl, and what we will do here in this tutorial is illustrate this with a practical application in climate sciences. So in order to understand how powerful this idea is, let's define our own functional data type from scratch in Julia. Here we load the three operations of the Hilbert space from the linear algebra module so that we can define these operations for our new type. We define our functional data type, which is just a wrapper for a data array. And then we define the three operations. We define the scalar multiplication between a number and a function, and that's going to be a new function, which is just the data scaled. We define the vector addition between two functions as a new function, which is just the sum of the underlying data arrays. And finally, we define the inner product between two functions, which is a scalar given by the inner product of the underlying data. For convenience, we also add a method for the show function so that whenever Pluto returns a function object, it displays it with Unicode characters. We can use this type to get intuition about weighted combinations of functional data. For example, imagine that we are looking at weighted combinations of this form, that is convex combinations, with this parameter lambda in 0 and 1. So I can create here two functions, f, which is the sine from 0 to 2 pi, and g, which is the function of cosine from 0 to 2 pi. And then I perform this linear combination of f and g, and I can manipulate this parameter lambda to see how this function is morphing. As you can see, the shape of the function f, this sine function, is morphing into the shape of the function g, the cosine, as we increase lambda from 0 to 1. And this deformation is quite smooth. Informally, we say that the scalar multiplication and vector addition determine how these objects in the Hilbert space morph into one another. Let's make this example even more concrete, and let's grab some real data from meteorological stations in Brazil. We'll be using the dataset by the Instituto Nacional de Meteorologia in Brazil, which provides real-time hourly or daily measurements of various climate variables such as temperature, wind speed, etc. Here we use the inmet.jl package to query this data directly from Julia. So I get the metadata for all the stations as a table, and I filter all those stations which have a situation that's operating. After I have all the operating stations, I just retrieve their name and then the longitude and latitude without units. This is what we get here. Approximately 400 stations that are still operating with their longitude and latitude coordinates. Because InMat imposes a download quota on the general public, we'll subsample the stations at random, and then we'll only download temperature data from two given dates here, so 2 weeks, starting from 1 of February to 14th of February, so the 2 previous weeks as we record this tutorial. The way it works is super simple. We just fix the seed here so that the subsampling procedure always returns the same subset. And I subsample all the stations, a max of 80 stations for this example. And then I loop over the stations and get the time series using the name of the station, the start date, and the finish date. This gives us a set of pairs of stations with the temperature time series, and then I can filter all those that are still with valid measurements, that are still producing numbers and not missing values. So here we get a collection of stations. There are a couple of stations here, and you see that this InMat package already returns measurements with proper units. So here is a time series of temperature data in degrees Celsius. We will convert the units from degrees Celsius to Kelvin to work with an absolute scale, and that's super easy to do with the Unifil.jl package. So I convert the units from Celsius to Kelvin in my data frame, and that's what we get. And finally, we will use our just created functional data type to show how we can interpolate functions. So here I map for each column of this data frame our functional data type, and this produces a set of functions of temperature measurements in approximately 40 stations in Brazil. The final step is to georeference this data set so that we can perform geospatial interpolation. So what I will do here is I will create a data frame which contains the name of the stations and the functions that I've just instantiated above. And then I'll do a left join with the metadata on the name column so that I can pull in the latitude and longitude coordinates. After I have this table with the functions and the longitude and latitude, I can georeference this table with these two coordinates to create a geospatial table. I have the name of the station, the corresponding function that was measured at that station, and the geometry, which is in this case a point with longitude and latitude coordinates. We can visualize all these stations in the map very easily. We use the geotables.jl package to download automatically all the polygons of states in Brazil when you pass this children equals to true. And then we visualize the domain of the Brazil map, that is the polygons, the domain of the functional data, a set of points, and that's how they look like. So in order to see how things work just out of the box, let's go ahead and compute the empirical variogram of our functional data. We can say the empirical variogram of the functional data, and I say that I want the variogram of the column fun, which is the column where we store the functional data. As you can see, this procedure works out of the box, even though we have a column with functional data type that we have just created. Not only that, notice that this procedure also keeps track of the units. So we started with measurements of temperature in Kelvin, and now we have our measurements of variogram or variance in Kelvin square. We could have detrended this data set to properly work with the residual process, but that's not the goal of this tutorial. So I'll just proceed and feed a theoretical model for Hilbert-Kriging. So we can just take our empirical variogram G and ask to feed a Gaussian variogram model on this empirical variogram and use optionally this weighting function here, which is a exponential decay. So I get my original empirical variogram, and then I plot next to it the theoretical model that was fitted with a Gaussian variogram model. Finally, we can define our estimation problem for the states of Brazil. So I can create my estimation problem as a table with functional data, and I want to estimate this time series at polygons, the states in Brazil. So I'll pass the domain of the Brazil map. And I want to estimate the variable fun. There are 27 states where I want to make the prediction of the functional time data or the time series, and I have 46 stations with measurements of functional data. We can then create the Kriging solver as usual, saying that the variable fun will have a variogram given by gamma that we have fitted above, and I'll say that I want to just use the nearest 10 stations in my estimates. I can solve the problem with the solver, and we get here all the 27 estimates of functional time, functional data at the states of Brazil, and their corresponding estimation variance in Kelvin square. Here is the geometry of the states, which are these polygons. And the interesting thing about the Hilbert-Kriging approach is that unlike multivariate approaches that treat functional data as sequences of correlated variables and then make sure that the correlations are preserved or modeled explicitly, Hilbert-Kriging treats these functions as objects with a single, perhaps exotic variogram model. I have a few remarks. We say that GeoStats.jl leverages Julia's powerful dispatch system to generate high-performance code for any Hilbert space, functional data, compositional data, or any custom Hilbert space that the user provides. And additionally, it has very nice features. As I showed, it propagates units properly, so it can automatically identify the units of the variogram or variances in the Kriging system automatically from the units of the data. And it also does a very interesting and change of support here that's not covered in this tutorial. It will be an upcoming tutorial. But in order to find this time series on the states, we need to integrate the measurements at the points over these polygons. And GeoStats is doing this automatically for the users by integrating the point variogram that was specified based on the points for each of these different polygons. I would like to point out that these features would be extremely hard to implement in any other programming language. We are really using the Julia's dispatch system to get these features right. And if you want to look at other more advanced examples of Hilbert space, see the coda.jl package for compositional data. I hope you enjoyed and see you in the next tutorial.